Hi, I'm Carolina Alvarez.
I'm Donald Williams.
I'm Brianna Gaviria.
And I'm Christian Lombardi, and we are Team 2, the Doodlebots.
In this project, the goal of the experiment is to use an Arduino board and the provided sensors to practice the calibration of the equipment, along with the integration of a servo motor with two of the sensors.
In this experiment, it was required to calibrate a servo, water level sensor, and an ultrasonic sensor, and a thermistor. To demonstrate the required results, the water level sensor and the ultrasonic sensor needed to both have 10 datasets, while the thermistor only required 3 datasets to all show an accurate calibration curve.
To meet the requirements, the team will show how to set up each of the sensors. The presentation will contain wiring diagrams and a video representation as visual aid.
Once wiring is complete, any issues encountered will be discussed along with a solution to fix it. After assembly is completed, the videos of the sensors properly functioning will be demonstrated in the calibration steps. The servo has 3 wires, of which the brown one is the ground wire and should be connected to the ground port of the Uno. The red one is the power wire and should be connected to the 5-volt port, and the orange one is the signal wire and should be connected to the digital 9 port.
To assemble, you will connect the brown wire to the ground pin on the water sensor, the red wire to the positive pin, and then the yellow wire to the S pin. Then connect the brown wire to the ground port on the Arduino, the red wire to the 5-volt port, and then lastly the yellow wire to the A0 port. An issue faced was since the max distance of the water level was set, a multiplier and a divisor were needed to translate the code correctly. Another large issue faced was getting the sensor to translate the code and determine the measured distance. Using a ruler and placing tape on the back of the sensor to measure the data wouldn't record accurately. Instead of taping the sensor to the inside of the cup, it was lowered to the desired distance and was the only way for the data to come out accurately.
Connect the yellow wire to the VCC pin in the 5-volt output. Then connect the purple wire to the trig pin and the digital 12 port. Then connect the blue wire to the eco pin and the digital 11 port. Lastly, connect the green wire that goes into the ground pin and the ground port.
There were several issues that were encountered while setting up the sensor with its corresponding code. First was the unmatched baud rates when using the serial motor function. Next was not selecting the correct library to be attached. Lastly, the largest issue faced was translating the distance sensor's readings to the servo motor. Shown here, we use these variables to declare the servo into our code. The following lines are used to initialize the servo respective to the sensor. Using the max distance global set to 180, we were able to easily translate linear distance recorded from the sensor to the 180-degree curvature without using a multiplier or divisor to distribute the angle evenly when it writes it to the servo itself.
In the Arduino Uno R3 starter kit, the procedure for the thermistor sensor is provided containing the wire setup, coding, and visual outcome. Since the steps for this sensor are extensively long, the participants will be presenting a finished product that was followed through the text and diagrams given.
The only issue encountered was within the code. The team had to add an external library file so that the LCD screen would run properly. The other issue had to do with the text actually appearing on the screen, which was resolved by slightly turning the potentiometer until the text appeared.
When the code successfully runs, the servo motor will move 180 degrees back and forth as shown in the video.
When put into the water, the routings and the sensors that can change with the change of the water's depth. Then the signal of the water's depth is converted into electrical signal, showing the change in the water's depth throughout the serial monitor.
With the servo being added to the water level sensor, it is shown that as the sensor is being dipped in the water, the reading is demonstrated by the servo and can be verified with the serial monitor.
When using the device, place an object in front of the sensor to measure the length. The data collected is then represented in the serial monitor window. Once the servo is incorporated, the results are not only seen in the serial monitor, but can also be visually represented with the servo moving.
As seen in the video, the thermistor was calibrated since it is able to translate the temperature and have it displayed on the LCD screen. The main principle learned in this project was assembling the 3 different sensors by the participants, along with collecting and calculating sets of data. The data collected determines the average trend lines for how each of the sensors should react, but if any data were to show a notable distance away from the natural curve, it would be flagged as an error. The 2 different types of errors found in the datasets were hysteresis and zero shift. These errors were tied to several possible sources of error, along with the resolution for each sensor used.
The ability to construct and wire components is something that is seen all the time in engineering. There are many examples in the industry that exemplify the combination of components to work together as one whole unit. One great example of multiple components working together, such as electrical components, sensors, and programming, are rockets. This is probably one of the most popular examples in the industry due to how sensitive and precise the build of these space vessels have to be, since they are traveling from space and back with passengers.